In this video, we are going to study the Poisson distribution. Let's assume that you are working in an insurance company and you are evaluating whether you should provide services to some oil company. You pull up some old data on that company and you found out that on average they have, let's say, lambda number of accidents per year, let's say 3 accidents per year. Now, to evaluate whether you should provide services to that company, maybe you are looking for probabilities that number of accidents per year are greater or equal than, let's say, 5. Or maybe you are looking for probabilities that the number of accidents per year are equal to 4 or some value of random variable x that is going to model the number of accidents per year happening in that oil field. Now, basically what we are looking for here to know the values of these probabilities, we need to know the PMF of random variable x. We need to know probability density function of x. Now, all you know is that on average they have 3 accidents per year, and you need to model the PMF of that random variable x. To do so, let's assume that you know a little bit of calculus and but the binomial distribution from video lecture provided on the Moodle. Now, you can start off working in the following way. So we need to find the number of accidents happening in a year. Now, you can divide this interval of this year log interval into the following n equal pieces, where n is, let's say, large. Then we can look at each of that sub-interval of our 1 year log interval as a single trial in our binomial distribution. So it's like throwing a coin n number of times, where probability of each coin is given as, let's say, of landing on heads is equal to small p, where coin landing on heads will mean that we have an accident happening in that time interval. Let's say if you are splitting your year-long interval into the days, then you have 365 intervals. If you are splitting them into seconds, it's even better. So we'd like this n to be as large as possible. If n is as large as possible, if we are keeping our value of lambda, which is 3 accidents per year, constant, then p should be small. Then p is going to be small. All right. Now, we know that this model here is modeled by binomial distribution. Then we are looking for PMF of binomial distribution. So we are looking for probabilities that random variable x is taking on some value k, where x is a binomial random variable, which is given as n choose k multiplied by probability of a success. In that case, success means that we have an accident happening on a single trial. So an accident happening in that given subinterval, in that given second or day, the smaller that interval, the better. P to the power of number of successes, k multiplied by probability of failure to the power of n minus k. Now, since x is a binomial random variable, we know that expected value of x is equal to np. Now, expected value of x is a number that is going to show what is the average number you should expect, the average number of accidents you should expect in that year, which is given by our parameter lambda. So from here, we can derive the probability of p. probability of an accident given in each subinterval, which is lambda over n. Now, let's keep working. Let's replace the value of p here with lambda over n and choose k multiplied by lambda over n to the power of k multiplied by 1 minus lambda over n to the power of n divided by, so I'm gonna do several manipulations with the factors here. You will understand why the reason of these manipulations a second later. So I'm going to express that term as 1 minus lambda over n over k. So it is the same as this term over here. Now this is equal to, let's expand that coefficient over here as n factorial over k factorial n minus k factorial multiplied by lambda over n to the power of k multiplied by, so this term here, I'm going to, let's deal with that term first. So this is n minus lambda to the power of k. So this is n minus lambda to the power of k. Then we have n to the power of k here. So those two will cancel out in a second. Multiplied by, with this term, we are going to deal it in the following way. 1 plus 1 over minus n over lambda. It might be confusing why am I transforming them in the following way, but it will be clear in a second, right? To the power of minus n over lambda. So I need this term to be the same as this one, so that should be to the power of minus lambda then. So those two will cancel out. Now let's keep working. So the stuff that is going to cancel out is following. So here we have n multiplied by n minus 1 and so on. So I will cancel out some part of this factorial here with that factorial over there. So this is n minus k plus 1 over k factorial. Lambda to the power of k. In the denominator, I'm going to have 1 minus lambda to the power of k multiplied by this n to the power of k will cancel out with this n to the power of k here. So that will be lambda to the power of k here. Multiplied with that thingy over there. 1 over minus 1 over lambda to the power of minus n over lambda. Let me make this bigger. To the power of minus lambda. Now, so we started with probability of random variable x being equal to k. So the start of that is probability of random variable x being equal to k. So my next step is going to be the following. So we are going to take a limit from both sides as n is approaching to plus infinity. So I said that we want this n to be as large as possible. So let's take a limit as n is approaching to plus infinity. From both sides. And let's see what's going to happen. So first, I'm going to factor out the terms that are invariant of n. So here I have k factorial. I have lambda to the power of k. In those terms, I have n. And in these terms, I have n appearing. So this is equal to limit as n is approaching to plus infinity. No, let's factor out lambda to the power of k over k factorial first, multiplied by limit as n is approaching to plus infinity. Now let's pay attention to that strange term that I have written before. Now limit as n is approaching to infinity of that term is equal to the e. So this term here is then e to the power of minus lambda. Next, let's pay attention to this fraction over here. This fraction over here can be expanded as follows. We have k terms in the numerator, n minus 1 multiplied up to n minus k plus 1. So there are k terms over n minus lambda. So I'm going to write them down in the following one, n minus lambda. So k terms in denominator 2. Now, if you pay attention to these terms, as n is approaching to plus infinity, those can be regarded as some constant. This ratio is going to be equal to 1. So limit of that ratio is going to be equal to 1. So all we are left with is then, so I can remove the limit sign now. This factor over here, this huge fraction over there is equal to 1. This brackets here is equal e to the power of minus lambda. Now, so what I got then is that limit as n is approaching to plus infinity of probability of x being equal to k can be calculated as lambda to the power of k over k factorial multiplied by e to the power of minus lambda.
The result that we have derived just now is known as Poisson limit theorem. It was obtained by Poisson in 1837, and in the first 50 years it was used purely by its face value to simplify the calculations of binomial probabilities. If you take a look at the PMF of binomial random variable, so I have here, it involves the calculation of the following binomial coefficient. And in the case when n gets large, these calculations are very cruelsome. And calculating this expression here is much easier since it involves only one factorial term and it doesn't involve n factorial term in numerator. However, Poisson limit theorem found a new light after 50 years in the form of Poisson distribution. We use Poisson distribution to model situations where we have to find probabilities concerned with occurrence of some events per unit of something. And by unit of something, I mean unit of time, as we have seen in our example on accidents on oil field, per unit of time, or it can be per unit of area, volume, and etc. So random variable x is set to have Poisson distribution if it has the following PMF: e to the power of minus lambda, lambda to the power of k over k factorial. So to find probability that our random variable x is equal to k, we'll use the following PMF, and random variable x here denotes the number of occurrence of some specific event. Now let's take a look at a couple of examples. Also, expected number of Poisson random variable is equal to lambda, and variance is also equal to lambda. The derivation of these are rather straightforward, and I will upload this to Moodle. Now let's solve a couple of examples. We have a liquid medium with concentration of some particles in it being equal 10 particles per milliliter. So 10 particles per milliliter. Then we withdraw 1 milliliter of that liquid. And the question is, what is the probability that exactly 8 particles are withdrawn? So we are looking for probability that x is equal to 8, where x is Poisson random variable with the following parameter. So now the question is to find the parameter of that random variable. We use the following notation to denote that x follows Poisson distribution. In a case when we are working with Poisson distribution, the only parameter that we are going to need is lambda. So now let's find lambda in that case. So we have 1 milliliter of liquid withdrawn, and on average it has 10 particles in it. So lambda is equal to 10 in that case. Now, to find probability that my random variable x is equal to 8, we should use PMF for Poisson random variable with parameter lambda equal to 10. So e to the power of minus lambda, e to the power of minus 10, multiplied by lambda to the power of k, 10 to the power of 8, k is equal to 8 in that case, divided by k factorial. So divided by a factorial. And that expression is approximately equal to 0.11. So the probability that my liquid has exactly 8 particles is 11%. Now let's take a look at another problem. All right, so again, we are working with the liquid and concentration of particles in it. Now we have 6 particles per milliliter. Then we are withdrawing 3 milliliters of that liquid. What is the probability that exactly 15 particles are withdrawn? So probability that x is equal to 15 particles, where x follows Poisson distribution with the parameter lambda, which in that case is going to be equal to 3 multiplied by 6. So there are 6 particles per milliliter. However, I am withdrawing 3 milliliters, and the number of particles that I should expect in that volume of liquid withdrawn is 18 particles. So my parameter lambda is equal to 18 in that case. Now again, using PMF for Poisson distribution, e to the power of minus lambda, lambda to the power of k to the power of 15 over 15 factorial, which is approximately equal to 0.078. So probability of that is given as 7.8%. Now let's take a look at yet another example. So now we are going to model the number of cars that pass through a certain intersection during a fixed time interval. assume that the mean rate is 5 cars per minute. So 5 cars per minute. Find the probability that exactly 17 cars will pass through the intersection in the next 3 minutes. So the number of cars that I should expect to pass in 3 minutes then is equal to 3 multiplied by 5, 15. So my parameter lambda, which is expected number of cars I should expect to pass in that time interval, is equal to 15. Then I'm looking for probabilities that random variable x is equal to 17. Given that x follows Poisson distribution with lambda equal to 15. Now again, substituting values in our PMF, e to the power of minus 15, 15 to the power of 17 over 17 factorial. So this is approximately equal to 0.085. So probability of that is approximately 8.5%.